In this episode, we're going to be looking at the Doppler effect and how it impacts the way that waves travel. Believe it or not, you already know what the Doppler effect is. Here's why. So you've probably heard that before. Maybe a car horn, a police siren, a fire engine, something moving past you with a loud sound. So the first question would be, what did you notice about the sound of that car horn? So probably now you can say the car horn changed, the sound changed. But the question would be, how did it change? Same car horn, right? If the car wasn't moving, the horn would sound the same, right? You would hear it as a consistent sound. So what really changed? What was the change? Let's look at another example. So once again, we have a horn that appears or seems to change its sound. Now let's break down exactly what is being changed when we say the sound. I don't know how familiar you are with music or playing an instrument, singing, but frequency and pitch have a lot to do with how high a note is or how low a note is. Think of a piano with 88 keys. The keys on the right-hand side, right, all the way on the right, are going to be a higher pitch than the keys on the left-hand side, which are going to be a lower pitch, bass notes. That's really determined by the frequency in the piano wire kind of vibrating back and forth, right? The tighter the string, the higher the note. So getting back to the train, we have a moving train moving towards an observer, the person with the camera, and we hear a change in the pitch. Let's watch and listen one more time. So how did that sound change? Let's talk about it in terms of pitch. All right, as the train moves towards the observer, the pitch is high because it's coming towards you. So it's a higher sounding horn, a higher pitch, like a higher note on an instrument. As it moves away, the pitch gets lower. As it moves past you and moves further away, the pitch drops to a lower note. So what we're talking about is called the Doppler effect. And the Doppler effect is an important physical phenomena that not only helps us understand sound, like you saw, but it also helps us understand our universe. And I'll show you why. So the Doppler effect will occur with all forms of waves, whether they be sound waves, whether they be light waves, whether they be vibrations, right? All kinds of waves. And this is basically how the Doppler effect occurs. Say this dot represents a wave source. A fire truck siren, a light from a star, a duck in a pond. They're all emitting waves, and those waves go in all directions, same wavelength, same frequency. But if I move my source to the left, they bunch up in the direction it's moving. On the opposite side, they're spread out. That's the Doppler effect. So let's look at a case of vibration waves. A duck in a pond. If I asked you what direction this duck was moving, you would answer with to the right. Now, how did you know this? Probably because his beak is pointed in that direction, right? He's facing to the right, so obviously, probably. But there's another way to tell. Let's look closely at those ripples. Right underneath his beak, those waves are bunched up. And that shows that the duck is moving in that direction. Because as the source, which is the duck making vibration, moves, the waves bunch up in the direction it's moving. So let's move on to light waves, right? An electromagnetic energy source, so this can really apply to any electromagnetic energy, but we'll focus on light. So here's our visible light source. It could be a light bulb, it could be a star, it could be our sun. Either way, the circles that are surrounding my light source represent waves, and those waves are all the same frequency, they're all the same wavelength. So the light that's being produced is white, right? And it's going in all directions. I show it left and right, but it's really being emitted in all directions, which are what the circles are meant to represent. Let's say I move my light source. So my light source moves to the left. Well, what happens? On the left side, I have waves that are now bunched up. All right, I have a more frequent waves set of waves, and I also have a shorter wavelength because they're coming more frequently. So the color of my light will shift to more violet. And if you remember from our electromagnetic spectrum, that makes sense because violet has the shortest wavelength of the colors of the rainbow. Now on the opposite side, the waves are now spread apart. So the color is going to shift there too. So instead of being white, it's going to be more red. And that's because red is on the far right of this spectrum, meaning it has the longest wavelength. So those two things are very important. And in our next video, we'll be talking about how we use this to determine that the universe is actually expanding. So more on that later. Let's move on to sound waves. Our last example of how the Doppler effect works, I'm going to let a famous physics professor do the explaining.
I will first make you listen to the 4,000 hertz without my moving. Can you hear it? Very high frequency. Is it painful, really? High frequency. Most of you are young enough, you should be able to hear 4,000 hertz. Okay, now I'm going to move it to you, 1 meter per second, and away from you. Did you hear it? Once more. When it comes to you, it's clear that the frequency goes up, and when it moves away from you, the frequency is down.
So going back to our look at the car and the train horn, when it's moving towards you, the waves bunch up, right? So therefore the wavelength is shorter and the frequency is higher, so the sound, the pitch goes up. And when it moves away from you, the opposite happens. The waves are more spread out, the frequency drops, and therefore the pitch drops. So this physics professor showed that with moving the tuning fork back and forth. So in summary, the Doppler effect is the shifting of wavelengths when the distance between the observer and the wave source is changed. And this is applied to vibrations, as well as sound, and also electromagnetic energy. Thanks for watching.